Welcome. Here is a new problem at your screen, as you can see, and perhaps the concepts we are going to use to solve this problem are equation of continuity and Bernoulli's theorem. But let me read you the statement of the problem first, and it says a water jet enters a horizontally standing channel. You can see here it's something like that, with a semicircular cross section in a vertical plane passing through the deepest part. Of course, I can understand that. Calculate the ratio of amount of water flowing out of the two ends of the channel as a function of the angle of incidence of the water jet. Yeah. So, to solve this problem, however, the phenomenon under study, that is the penetration of the water jet into the channel, it's spreading and splitting into two parts, is in general quite a complex and complicated process. So we need to use some simplifying assumptions, and so hereby we assume that the flow is laminar, vortices are not formed, not to a significant extent, and we neglect the internal friction of the water, that is what is called viscosity, property of viscosity, and further assume that the flow is fast enough that the change in potential energy is not significant in addition to the kinetic energy, because we are going to consider the change in kinetic energy, but we have to neglect the change in potential energy, otherwise things are going to become very much complex. So the validity of these assumptions cannot be strictly verified, and obviously experimental conditions can be set up where these conditions are not met. However, the opposite case also exists. What I'm trying to say you that for a fairly fast but not too fast flow, or for a not too narrow liquid jet, the described conditions can be considered a good approximation. So under such an approximation, I'm going to solve this problem. And to do so, let us denote the velocity of the water jet entering the semicircular cross section as V, and the velocities and its cross section areas of the water jet flowing out to the right and the left. I'm going to, and also I need to consider its cross sectional area. I'm considering it as A, and right, I'm going to consider this velocity as VR and its cross sectional area as AR, and in a similar manner the velocity of the water jet flowing out to the left by V left, and its cross sectional area by AL, left and right. And I'm going to write down or I can consider like this, that in a unit of time, per unit time, a volume of water VA flows through the cross section of the water jet, that is volume of water per unit time. I can always write it VA, velocity multiplied by the area of cross section, And our task here is to determine the relationship between the ratio, that is something like VL AL divided by VR AR. I'm just formulating the problem, and the angle of in terms of angle of incidence alpha. And so I'm going to first write the equation of continuity, and that is basically based on the conservation of mass. And water can be considered as an incompressible fluid. So I can write the equation, and I would like to take the density of water as rho, so that I will be able to write its equation of conservation of mass, that is also called equation of continuity. Simply incoming water per unit time, incoming volume per unit time is VA, and if we multiply by the density of the water, it becomes mass of water per unit time. Incoming mass of the water per unit time from the jet here is VA rho, and it is going to divide into two parts, so I can write here VR AR rho plus VLAL rho, and this is our equation 1. And I think I can also write the conservation of momentum in horizontal direction, and of course horizontal direction. So I will have to write the horizontal component of momentum of the water flow, water jet per unit time, simply as V A rho multiplied by its mass per unit time, they were multiplied by its velocity in horizontal direction, that will be V sine alpha. And in the similar manner we can write VR AR rho VR, that is the momentum per unit time, linear momentum per unit time of the water flowing to the right. And for the left we can simply write as VLAL rho multiplied by VL, and this is my equation number 2. And since I can also consider this thing, since under the described conditions the channel does not exert a horizontal force on the fluid, neglect the internal friction, viscosity is not present there, so the kinetic energy of the fluid flowing through it does not change either, because we are not taking the change in potential energy into account. That means the potential energy, the kinetic energy of the fluid is also constant. And I can write an equation, although I don't need this, but I can write it also as half kinetic energy per unit time. This is so that I can write V A rho, this is mass per unit time, V square of the incoming water, and right and left I could write in the similar manner half VR AR rho VR square plus half VL AL rho multiplied by VL square as equation number 3. But the system of equations from 1 to 3 is not yet sufficient to determine the desired water flow rate. So we must use some additional law of physics, and we know that for frictionless laminar fluid flow the Bernoulli's equation is valid, and according to which we can simply write as half rho V square plus pressure P plus rho GH being constant. This is equation number 4, basically Bernoulli's equation. And the value of expression is constant along a streamline, we know that. So let us apply this law to one of the streams connecting the water jet entering and the water jet leaving on the right or on the left side. But for now I am going to take I'm going to apply this law to one of the streamlines connecting the water jet entering and the water jet leaving on the right. And considering that we neglect the change in potential energy, that is this term, and we also know that the pressure on the water jet is equal to the external air pressure, so this term will also get materialized. And so Bernoulli equation says that half rho V square should be equal to half rho VR square, and that means the law itself suggests that V must be equal to VR. And in the similar manner, if we apply the Bernoulli's theorem to the incoming water jet and the water jet moving towards left, we will also get that V is equal to VL. And it simplifies everything else. And now we are going to use all the equations 1, 2, 3, 4, 5 together, and mostly I would like to use equation 1 and equation 2. And I needed to find out this ratio, VL AL divided by VR AR, and it is now simply, it looks like simply AL by AR. And if we use both of these equations, putting VR equals VA, VL equals V, VR equals V, VL equals V, and using equation number 1 and 2, we will get the values of AL and AR simply as I did it. So you can do it. 1 minus sine alpha divided by 1 plus sine alpha. And this is the desired ratio, I think. We needed to solve this problem. And you can see here, if alpha is equal to 0, then the water jet will obviously split into two equal parts. And in case of alpha equal to 90 degree, it will flow entirely forward. And in the intermediate cases, the amount of water entering will be divided in the ratio corresponding to this equation. So this was the problem, and this is the solution, and we have solved it and left it you as an exercise to find this. And this can be your entertainment and a bit of use of energy. Thank you very much for watching.